In everyday life, time feels like a constant flow, a river carrying us from the past to the present to the future. Clocks measure it, we experience it, and events seem to line up in a strict order. In classical physics, time is treated as an absolute backdrop, the same for everyone, everywhere in the universe. This was the view of Isaac Newton, who imagined time as a universal ticker that never changes pace, like an invisible metronome for the cosmos. In Newton's equations, time exists independently of the things happening in it. Just like space is the stage where physical events play out. But in the early 20th century, Albert Einstein changed that view forever with his theories of special and general relativity. Einstein showed that time is not absolute. It has intertwined with space into a single entity called spacetime. According to relativity, how fast time passes depends on your motion and the strength of gravity around you. For example, if you're moving close to the speed of light, or you're near a strong gravitational field, like a black hole, time for you will run slower compared to someone far away. This is called time dilation, and it is not just theory. It has been confirmed with precise atomic clocks and even affects GPS satellites in orbit. This means time is not some universal flow. It's flexible, personal, and depends on where you are and how you move. When we get to the world of quantum mechanics, time becomes even more mysterious. In quantum theory, the equations often treat time as a fixed background parameter, just a number you plug in to see how a system changes. But when physicists try to combine quantum mechanics with general relativity into a theory of quantum gravity, something strange happens. Time can disappear from the equations entirely. For example, in the Wheeler-DeWitt equation, a candidate for describing the entire universe at the quantum level, there is no explicit time variable. This has led some scientists to wonder if time is not a fundamental part of reality, but instead an emergent property, something that only appears when we look at the universe in a certain way, like how temperature is an emergent property of many moving particles. From a modern physics perspective, there are two main possibilities. One is that time is real and fundamental. It exists at the deepest level of the universe and is woven into the fabric of reality. The other is that time is an illusion, arising from the way we perceive change and organize events. In the block universe view, supported by relativity, all moments, past, present, and future exist equally, and the flow of time is just a human experience, not a physical feature. In this picture, you can imagine the universe as a four-dimensional block of spacetime, where now is just a slice we happen to be experiencing. So does time exist? In physics, the answer is complicated. It definitely exists as a concept we can measure and use in equations. But whether it exists as a fundamental ingredient of the universe, like energy or matter, is still an open question. The deeper we go into relativity, quantum mechanics, and cosmology, the more it seems that time might not be what it appears to be. And if we ever solve the puzzle of quantum gravity, we might discover that time, as we know, it is only a shadow of something even more fundamental,